wrong?
I did. I told you something wrong.
Oh my god.
My bad. Okay.
That is my head.
Y'all know, when I was dreaming about buffer solutions last night, I also was explaining the titration curve of the buffer solution. And then it's literally like subconsciously when I woke up this morning, I said, but that was it. You know, like you just feel like something was wrong sometimes when you wake up. It's like a bad dream or something. Like I woke up not with like a bad dream feeling, but with a something is wrong. And I was like, because I taught that wrong. I'm an idiot. So we're going to fix it. All right. So, does everybody remember the titration curve?
Yeah.
Okay. Does everybody remember how we said to find the equivalence point?
Yes.
Yes, we take this and we go halfway and we say this is the equivalence point, right? And so we said this is where the moles of acid is equal to the moles of base, right? Right. We said that. I know we did because I said it to you. Then here's where things get a little tricky. We talked about the half equivalence point. Remember when we talked about the half equivalence point? Let me correct the half equivalence point, okay?
I didn't understand this when you actually taught it.
Okay, well this time it's going to make sense in the name of Jesus.
Yeah.
All right.
I'm here now.
So at the equivalence point, we have the certain volume that we added, right? We added a certain volume to get to the equivalence point, and so that's listed across the bottom, volume, and then our pH is listed at the side, all right? To find the half equivalence point, here is what you do, okay? You take the amount of milliliters that you added to get to the equivalence point, and you cut them in half. Because at the half equivalence point, you've added half the amount. So let's just say that we had added 12 milliliters at my equivalence point. So at the half equivalence point on the graph, it would be when I had added 6 milliliters. Does that make sense?
Yeah.
Okay, so then I would find, so if this is where I added 12, I would say, okay, well, here's 12. Where was I at when I added 6?
You just go straight.
Okay, and so then I would find where I added 6. So that would be my half equivalence point. Find my pH, and then that's where I know that pH is equal to pKa.
So it's not like in the spike.
You want us to write it down, right?
What spot? I don't even remember.
Remember, we said it was like
She said
right
it was
there.
in the spike.
Yeah, so we said it was-
Let's not go back. Oh, really?
Yeah, it's not.
Oh, wow.
That's so much easier though.
It is easier, which is good. So we good now?
Yeah.
We feel great
Well, I
now?
mean, the 12's a little off, but I'll take that.
So if your equivalence point is at, you just cut it in half.
You just cut the volume in half, and that's where your half equivalence point is.
And then you just
Okay.
find where the pH.
Okay,
It's like
and then you
before,
just
it's kinda
find where your pH is, and then that's where at your half equivalence point is where your pH is equal to your
So
pKa.
much easier.
We feel better? Okay, good. All right.
How about that?
So that has nothing to do with what we're doing today, really, but
It's AP dirty.
it just clears up what did not make sense and should make sense now. So let's talk about 1972. All right. So 1972. So this was a question in 1972, and this is honestly kind of like what they're more gearing towards now. Okay, is the ability to explain and do you really know what's going on? So we're going to know what's going on today. So given a solution of ammonium chloride, before I go any further, do you see any chemical formula written out anywhere up there? No, so that means they're expecting me to know what ammonium chloride is, okay? Do I know what ammonium is? Yes, what is ammonium? NH4 positive, okay? Do I know what chloride is? It is Cl negative. So if I wrote those together, the charges would what? Cancel. And so we would just write this as NH4Cl. Easy enough? Easy enough. We should be able to get that. Now, because it's coming up in the next few units, not the next unit, but the unit after, let's do a quick review. What kind of bond is that? It is an ionic bond. How do I know it's an ionic bond?
It's there. One is an iron crystal.
Because it's a positive and a negative bonded together. Okay. So it is an ionic bond. And when it is an ionic bond, this is going to be important. We say that it forms an ionic crystal. And the better word that we use for an ionic crystal is what? We use it to make our food real tasty. Salt. Okay? This is going to be important for understanding this. All right? What additional reagent or reagents, so it's asking me what else? What other thing, what other substance do I need to add to this to prepare a buffer from the ammonium chloride solution? So before I could even answer this question, I need to understand what a buffer is, okay? So I need to know what a buffer is and how does it work? What's it made of? So a buffer is something that resists a change in pH. So that's what a buffer is. It's something that resists a change in pH. So if I add H positive, what happens to my pH? It goes down, right? Because it becomes more acidic. If I add hydroxide, OH negative, what happens to my pH? It goes up. It becomes more basic. So a buffer tries to keep that from happening. Okay? It tries to resist a change in the pH. Okay? So how does it do that? It does it by being able to take. So a buffer has to be able to remove H positive and OH negative. In solution. Okay. So it's got to be able to remove H positive and OH negative in solution. So a buffer is normally made of, okay, it's normally made of a weak base or a weak acid with its conjugate salt. Okay. So let's talk about this. Okay. So this, the ammonium chloride, is obviously my what? The salt, right? We just talked about this. So this has to be the conjugate salt. Okay. So a buffer, we said, normally consists of a weak base or a weak acid with the conjugate salt. So let's look at NH4 and Cl. What would the Cl come from? HCl, which is a what? Strong acid. So do I want to add that as one of my reagents? No, because that's a strong acid. The NH4 had to be a conjugate of what then? NH3. Okay, so what reagent would I want to add in here? I would want to add NH3 because NH3 is a what? Weak base. And so I want to pair it with the NH4Cl because that's going to be the conjugate salt. Don't get stuck on it. I'm going to make it make sense, okay? I promise. It's going to make sense. Just go with me for right now. So explain how this buffer is going to work. That's what they want me to do for A, B, and C. So how is it going to work? So let's pretend I've got a beaker. There's my water. It's in solution. Okay. So in this solution, I've got NH3 and I've got NH4 positive. Right? Right. So we've got NH3 and we've got NH4 positive. Why am I not adding in the Cl negative? Is the Cl negative in there? Yes, okay. I'll draw it in black. Okay, Cl negative is in there, but why am I not concerned about it?
It's just being.
Okay. Remember, we said strong are what? Spectators. So since that Cl negative would have had to come from HCl, we say that this is just a spectator. So really, it's floating in there, but is it ever going to change? No, it's just going to stay in there. So we would draw it in there. If they asked me to draw it, I would just show that it's not changing. All right. So what happens when we add strong acid? Well, essentially, when we add a strong acid, what are we adding? H positive, right? So a strong acid, what we're going to be adding is H positives. So I add a couple H positives in here. So we would expect the pH to do what?
Lower.
To decrease, right? We would expect my pH to go down and become more acidic. But remember, a buffer resists a change in pH, so how is it going to do that? How can I add H positive and my pH not change significantly?
Because you have the just the buffer.
Because I have the NH3. What is the NH3 going to do? It's going to react with this NH plus, and so both of these molecules are going to turn into what? NH4 positive.
So you're just gonna make more salt.
So I'm just making more salt.
What cancel out?
The NH3 canceled out the H positive. So that's why my pH did not change a lot, is because the NH3 took the H positive out of solution.
But if you don't have
Right.
enough buffer,
So eventually, so that's why when we did our lab with the weak acid, the strong base, okay, as it's going, okay, it's rising slowly. So the pH is going to increase, but it's increasing slowly because I've got a buffer. So as I'm adding it in, it's taking it out of solution, but eventually I'm going to run out of what?
alright, so we're
A
adding,
buffer.
okay, I get it now.
You see?
That makes sense.
Eventually I'm going to run out of buffer, and so then my pH
You guys have to get
is going to
slow.
spike. Do we see that? Okay. So, if I was to write the net ionic equation for this, how is this happening? Well, the NH3 is taking away the H positive, and it's making NH4 positive. So since I don't have this H positive in solution, then my pH doesn't change significantly. Does that make sense?
We would just write the equation for the answer.
Yeah. So B says, what happens when we add moderate amounts of strong base? So when we add strong base, we're essentially adding what?
OH.
OH negative, right? So when I add OH negative in here, I would expect my pH to do what?
Increase.
To increase. But if I put it in a buffer, it shouldn't increase a lot. Why? What's going to
You'll
happen?
make H2O and NH3.
I'll make H2O and NH3 because I'm getting so smart. Okay? So this NH4 is going to donate a hydrogen to this OH negative, and then we're going to make NH3 and H2O. So again, my pH doesn't what? It doesn't change.
Now, are there cases where you can add too much of a strong acid too much of a strong base?
So the net ionic equation for this would be so that's how a good buffer works, okay? It's able to resist a change in pH whether I'm adding a strong acid or a strong base.
So if you don't have the right buffer, you automatically you run out of your equation.
Yes, you should.
I guess you just-
Does everybody see how the buffer works?
It's freaking awesome.
So think about when, and this is just so you can understand the whole purpose of the lab, like what happened. So think about it, we had acetic acid, right? So acetic acid dissociates into H positive plus C2H3O2 negative, right? So here's my weak acid, here's my conjugate. Do we see that? All right. So we were adding in what?
Adding
NaOH. So essentially, remember, strong is a what? Spectator. So essentially, we were just adding in OH negative. So when we added in the OH negative, what was happening? This H positive is canceling it out, right? Okay. That would be why, remember that phenolphthalein, the indicator? When you would put it in there, when it would first splash in the water, you would see it turn what? Pink. Because we added that hydroxide, it was basic, it turned pink, but then the pink would do what?
Disappear.
It would disappear. Why is it disappearing? Because it's being taken out of solution.
That's awesome.
Do we see it?
So that's
We understand it? Okay, no, that's not C. That was just to explain the lab, so hopefully you saw it and you understood it and you got it. Okay, which is why, and we'll do that on the next one. I'll show you. Does everybody have this drawing? Because I'm about to erase it. We're good. So C says a portion of the buffer solution is diluted with an equal volume of water. How is that going to affect the buffer? Is it going to change the pH? No, it's not going to change the pH. Why is it not going to change the pH? Huh? It's actually not because water's neutral. I'm going to draw again just so we can see it, okay? So I've got NH3, NH3, NH4 positive, NH4 positive, right? So do I have a good buffer going right now? Yes. Can I neutralize an acid and a base? Yes. Okay. If I add water in here, now I added some extra H2O. Do I still have a good buffer? Yeah. Why do I still have a good buffer?
It's still there.
Because I still have a good ratio of base to acid, right? Do I still have a good ratio of my base to my conjugate acid?
Are they not? So the H2O is just going to say H2O and those are going to.
Yeah.
So.
So I didn't change anything, I just added more water. That's all I did. So the water's not going to bond with anything, it didn't change anything. So as long as my ratio of base to conjugate acid stayed the same, then I still have a good buffer.
You're just changing the overall, but not affecting
Right.
the ratio.
So
What's the-
equation?
No, you just need to be able to explain that as long as the concentration of my base to my conjugate acid, or it could be flipped around of my acid to my conjugate base, stayed the same, then I still have a good buffer. It's not going to affect the pH. Okay. What's the best ratio of my buffers? 1 to 1. Why is the best ratio for a buffer 1 to 1? There you go. It means I've got the same amount that I could neutralize an acid, the same as I could a base. Do we understand what buffers are a little bit better now?
So how would we put C into words?
See, I would just say that adding water does not affect the ratio of NH3 to NH4 positive, so therefore it will not affect the pH. Okay. Well, I feel better. I feel like I'm not going to dream about buffers tonight anyway, so hopefully you feel better.
Yeah, you did a good job.
Appreciate that, Joe. Everybody got that? We're ready to go? Alright, so let's talk about 1983. It says specify the properties of a buffer solution, aka what does a buffer solution do? We already talked about this. What does a buffer do? Resist a change in pH. Excellent. So that's what you would write for the properties of a buffer. If they ask you for the properties of something, they're asking you what does it do. It resists a change in pH. Okay. Describe the components and the composition of an effective buffer solution. Okay. Now, you could describe this any way you wanted to. I could say an effective buffer is a weak acid and it's what? Conjugate salt. Or I could have said it is a weak base and it's conjugate salt. Okay? Or I could have said, right? So, and vice versa. Okay, so I could flip this around and say it the other way. Or I can also take a weak acid and add about half the amount of moles of a strong base. Or I can take a weak base and add about half the amount of moles of a strong acid. Or I can take a weak acid plus a weak base. Now, would you have to write all of them on the AP exam? No. Okay, just choose one.
Just 2 seconds.
All right, just choose one. But you do need to understand that all of these can make buffers. Because we made a buffer in the lab by combining what?
NaOH and
We combined acetic acid, which is a what?
uric acid.
Weak acid. Plus, we combined it with what? NaOH, which is a strong base. Okay. And did we make a buffer? Did it resist a change in pH for a while? If you looked at Hope's graph, you would believe it. Okay. It resisted a change in pH for a while before it spiked.
Well, yeah.
So was this a good buffer? Yes. And it consisted of a weak acid plus a strong base. Okay. We're good? We're good. I'm feeling great. Okay. The names on part B, just take me over the top. All right. An employer is interviewing 4 applicants for a job as a laboratory technician and ask each how to prepare a buffer solution with a pH close to 9. Whoa. So now I want a pH close to 9. So not only do I want to create a buffer, I also want to create a buffer with a specific pH close to 9. 9 lets me know that I'm looking for a buffer that's what? Basic. Okay? Do you weak base, strong base with a pH of 9?
Strong base. Strong base.
I'm going to say weak base.
What? No.
All right? Let's talk about why.
I know what she's talking about.
All right.
Teachers are probably good.
All right. Our pH scale from 0 to 7 is considered what?
That's
Acidic. So a strong acid has a lot of what? H plus, right? So I would expect a strong acid to be somewhere down here because it dissociates a lot. Whereas a weak acid doesn't what? It doesn't dissociate a lot, so its pH would be more up here. Do we see that? Okay. So from anything greater than 7 to 14 is considered to be what?
Basic.
Basic, which would mean it has a lot of what? OH negative. So a strong base dissociates completely, so since it's going to have a lot of OH negative, I would expect it to be closer to 14, right? Whereas a weak base doesn't dissociate easily, so I don't get a lot of hydroxide, so I'm going to expect it to be closer in there. Do we see that? So a pH of 9, it lets me know that I'm looking for something with a weak base. Does that make sense? All right. So, which of these applicants has given the appropriate procedure? Explain your answer referring to your discussion in part A. Explain what is wrong with the erroneous procedures. No calculations are necessary, but the following acidity constants may be helpful. Acetic acid has a Ka of 1.8 times 10 to the negative 5th, and ammonium has a Ka of 5.6 times 10 to the negative 10.
Well, Dexter's got a strong base.
I think
so he's
Carlos
out.
C. Is it Carlos C?
You think Carla C? It is Carla C. Okay, so Carla C is the person that I would pick for the job. Okay. Carla C knows what she's talking about.
Archie
So-
wrote all this out. I don't know.
Why is Carla C's good? So let's talk about why hers works.
She has a salt and a weak base.
Okay, so she's got the weak base. Okay, and what else does she have? It's conjugate salt. Is NH4 positive the conjugate of NH3? Yes. Is NH4Cl a salt? Yes. So I see I've got the weak base plus the conjugate salt. We see that? We're good with that. Excellent. Okay. Also, we could look at the fact NH4 positive has a Ka of 5.6 times 10 to the negative 10th. Okay, so if I took the pKa for my pH, since this is raised to the negative 10th, and this number is greater than 1, I know my pH would be somewhere around less than what? 10. Do we see that? So you can look at it using their Kas too, right? But you don't have to. I'm just showing you in case some of you like to double check yourself. All right? Because she would be the one in the room that would want to double check herself. Everybody else would be like, "Yep, I'm going with this, and I'm good with it." All right. So let's look at Archie A first. Okay. Why is Archie A's not going to work?
You didn't even capitalize that.
So he has acetic acid, which is a what kind of acid?
It's no, we
There you go.
whoops.
Okay. He's got acetic acid, which is a weak acid. Is sodium acetate the conjugate salt of that? Yes. But he used a weak acid in its conjugate salt, so his buffer solution of his pH is going to be what? Acidic. It's not going to be basic. And we want it to be basic, right? So this one's going to give me an acidic solution. He's the one that understood what a buffer was but forgot the pH scale. And then Beulah B. Excellent. She put a strong acid with the conjugate salt of a what? A weak base, right? So she did a strong acid with the conjugate salt of a weak base. She's all messed up. That wouldn't even make a buffer. And then we've got Dexter D.
He used a strong base.
He used a strong base with a, what's NH3?
Conjugate.
What kind of base is that?
Base.
Weak base. So is that even a buffer? No.
So B and D are just hard.
Okay, yeah. So B and D don't know. Archie A, I mean, he was headed on the right track, just the opposite direction. Okay. He was on the right track, just going the wrong way. Does everybody see that? We feel good about that? Yay, we do. All right, we're probably not going to get finished with 2002, but we're going to try. We're not going to do the next one. This will be the last problem we work. Okay, it's 2002B. And I don't know. Let's see. We may get finished with it. We may not. All right, lactic acid is a monoprotic acid. What does monoprotic mean? Single. It only donates one hydrogen. That dissociates in aqueous solution as represented by the equation above. Lactic acid is 1.66% dissociated and 0.5 molar lactic acid solution at 298 Kelvin. For parts A through D below, assume the temperature remains at 298 Kelvin. So that just lets us know that temperature does not affect this at all. Okay, so probably they're going to make us find Ka, and they just want us to know that Ka will not change. It will stay the same through the whole problem. Okay. A says write the expression for the acid dissociation constant Ka for lactic acid and calculate its value. So I want an expression and I want the value of Ka. If you get nothing else right on the AP exam, I hope at this point you can write an equilibrium expression. Okay, so let's start with A. Can I write the equilibrium expression for this? Ka is equal to what? Products over reactants. So the concentration of my H positive times the concentration of C3H5O3 negative, all divided by concentration of H, C3H5O3. And that would have been a point on the AP exam. So you know you at least scored a 1. Yay! Knowledge. Alright, so did the expression, checked that off, got my point. But then it asked me to find the value of Ka. Okay? Now remember, even though you may not see it and you may not know what to do with the information, they did give you the information somewhere in the problem to be able to find Ka. Alright? So, what did they give me in the problem?
The malaria.
There you go. They gave me the percent that dissociated, and they gave me the molarity of the solution. What does percent dissociation equal to? Percent dissociation is equal to the amount that what? Dissociated divided by the initial concentration times 100. So I know the percent dissociated was what? 1.66. Okay? Do I know the amount that dissociated? No. That's X. Do I know the initial concentration?
Yes.
Yes. That's 0.050. And then I multiply that times 100. What's the first thing I want to do to get X?
To multiply.
I would divide by 100 and go ahead and get rid of that.
If you want to do it that way.
So then I get 0.0166 is equal to X over 0.50. So now what do I do to get X?
About 5 multiply 0.5.
I'm going to cross multiply. So then I get X is equal to 0.0083 molar. So that's how much dissociated. How does that help me find my Ka?
Because it's area.
That's my H positive, which is also my what? C3H5O3 negative. And what am I going to do on the bottom here?
It gives it to you the 0.5.
I'm going to do the 0.50, and what am I going to do with that X? I'm going to subtract X, right? Now, why am I not going to neglect it this time? Because I already have it. I already have the value of X, so there's no reason for me to neglect it. Do we see that? Do I need to write out the rice table? No, we're good. We know where I got that off of the rice table? Okay, good. So I plug that in, so I say that means my Ka is equal to 0.0083 squared divided by 0.0083, I mean 0.50 minus 0.0083. And so then I get that my Ka is 1.4 times 10 to the negative 4. So they would have given me a point for my expression. They would have given me a point for knowing that I had to find X and for getting the correct value. And then they would have given me a point for finding Ka. So I'm 3 points in. Most of my long free response are worth 9 or 10 points. I'm shooting to get how many of them? Half. Okay? So I want to get around 5 every time. If you can get more, you get more, because you know there may be some problems where you just can't hardly get any. Okay? We can do this. We can. Okay, so that's A. I'm good to go. Everybody got A? We did its value. We checked it off. And remember, you can write on your AP exam, and I definitely recommend doing it. Circle what you need to know and check it off as you find it. That way you don't write the expression and forget to calculate the value. So then B asked me to calculate the pH of the 0.5 molar solution. Can I find the pH? How am I going to find pH?
Opposite log of H positive.
Opposite the log of the concentration of H positive. Do I know the concentration of H positive?
Yeah.
Yes, I just found it when I found X. So I just say pH is equal to opposite the log of 0.0083. How many decimal places do I want? 2. So my pH is going to be 2.08 plus a point. All right, C. Says calculate the pH, which means I already know if I'm trying to find pH, I've got to know what? Concentration of H positive of a solution formed by dissolving 0.045 moles of solid sodium lactate and 2.50 milliliters of 0.5 molar lactic acid. Assume the volume change is negligible. So what does that mean?
We can
Significant.
It means that when I added in the solid sodium lactate to the 250 milliliters, we're assuming that the volume didn't what? Change. Okay, we're just assuming that the volume didn't change. So this time, let's write out our equation and set it up as a rice table. Initially, what's my concentration of my lactic acid? 0.5 molar, right? You did not just say that right there. What's my concentration of my acid? 0. What's my concentration of my C3H5O3 negative?
we did that. It's 0.002. No. It's not that.
Is it 0.045?
We used to have that.
That's the moles. Is that the molarity? No. Okay. Now, how do I know that this right here, the 0.045 moles, goes right here with this lactate ion?
What?
Because this is what? Sodium lactate. Anything bonded to sodium, potassium, or ammonium is always what? Soluble. Which means when we put it in solution, it automatically does what? Dissociates and dissolves. So this is going to dissociate into Na positive and C3H5O3 negative. Do I care about the Na positive? Nope. Don't care about it at all. So, whatever concentration that I added of the sodium lactate is the concentration that I added of my lactate ion, right? Yes? Okay. So I added 0.045 moles. Why can't I just write 0.45 down here in my rice table? It's not in molarity. Remember, molarity is equal to moles over liters. Okay? So, do I have the moles? Yes, 0.045 moles. But to get molarity, I've got to divide that by liters. How many liters do I have there?
250.
That's how many milliliters?
Just kidding. 1.250.
Yeah.
Just kidding.
So divided by 0.250 liters, which would be 0.18 molarity, and they would give you a point for that. So now, all I have to do is set up my rice table like normal, right? Okay. So my change, I'm going to lose X, gain X, gain x. So at equilibrium, I'll be at 0.50 minus x, and 0.18 plus x. Can I solve for x? How?
With the, yeah.
With my Ka. Do I know my value of Ka? Yes, I just found it up here, right? So my Ka is 1.4 times 10 to the negative 4 is equal to, what's going to go on top?
Your product, so you got a point, 0.18 plus x.
Excellent. And x divided by 0.50 minus x. What am I going to do next?
Neglect the x's.
Neglect the little x's that would make my life miserable. So now can I solve for x? Yes. So I would cross multiply and get 1.4 times 10 to the negative 4 times 0.50 is equal to x times 0.18. So then what would I do? Divide by 0.18. So then x would be equal to 3.9 times 10 to the negative 4th. And that gives me my concentration of what? H positive. So now can I find my pH like it asked me to do?
Yeah.
Yep. You can see pH is equal to opposite the log, 3.9 times 10 to the negative 4. So my pH is equal to 3.41. Now, there is an equation on your equation sheet. You know your AP equation sheet and constants? Okay. If you will get that out, and you know the section of equilibrium, I want to show you this equation, and you can use it as you please. Okay? We're going to stop here for the day, by the way, after I show you this equation. So you've got your AP chemistry equation sheet. If you look at equilibrium, do you see the equation that says pH is equal to pKa plus the log of A minus divided by HA? Everybody see that? So that's the concentration. So I could have set this up as pH is equal to, what's pKa?
That's also your
That's the opposite the log of what? My Ka value, which is 1.4 times 10 to the negative 4 plus the log of the concentration of, see where that says A minus? What's my A minus in this equation?
That
C3H5O3 negative, right?
one.
Okay. Because this is HA, that's my acid, and it went into H positive plus A minus. Okay, so there's my A minus. What's my concentration of A minus? 0.18 molar, right? Okay. Divided by the concentration of my acid, what was the concentration of my acid?
Just the
0.50. And if you plugged this into your calculator, it would give you 3.41. So you could have done it without an equilibrium table. I'm done for today. Okay. Hopeful, I will see you in just a few hours.